This lecture is going to be over linear accelerators and what do they mean for you as a radiation therapist. So what are the major components here? Well, we have the drive stand, we have a gantry, we have a treatment couch. Within the drive stand, we're going to have several different components, one of which is either going to be the Klystron or the magnetron. We're going to have a circulator, we're going to have a waveguide, and we're going to have a cooling system. So let's take a look at some of this here. The Klystron. If you remember back from the previous lecture that I had, it's a specialized electron tube that's designed to amplify microwaves for the electrons while in the accelerator structure. It's found in the high energy LINACs and it's very stable. Now the magnetron. The electron tube, which is the source of the microwave power. So the Klystron is going to magnify what's done in the magnetron. It's found in low energy accelerators, less expensive and more unstable than the Klystron. So what is the source of microwaves in your microwave oven? Take a guess, think about it. The circulator prevents microwave power reflected from standing wave accelerator from re-entering the Klystron. So it directs the radio frequency energy into the waveguide, and it's the link between the Klystron and the accelerating structure. Then the transmission waveguide. So it transports the microwave energy from the Klystron to the standing waveguide. Rectangular copper pipe filled with an insulating gas. And then you've got the cooling system. So it cools components by circulating water to the Klystron, the circulator, accelerator structure, as well as the target. So then you have the gantry, and it's responsible for directing the photon or electron beam at a patient's tumor. Controls to the gantry are located on the hand pendant or a dedicated keyboard on the outside. And of course, you have digital readouts, which tell you what's going on. So what all is inside the gantry? You have the electron gun or the gridded gun. You have the accelerator structure. You have the treatment head, the target or scattering foil. You have primary collimators, and you have the beam flattening filter. So you have ion chambers, you have secondary collimators, you have slots for beam shaping and modifying devices, electron blocks, things of that sort. And then you have the field light. So the electron gun is going to be responsible for producing pulses of electrons, which are synchronized with the microwaves injected into the accelerator structure. So within the accelerator structure, you've got a standing waveguide. And we went over standing waves. You've got the nodes and the antinodes that it creates. You've got highly evacuated copper tube that is precisely tuned. It's quite efficient, and entering microwaves are combined with waves reflected within the accelerator to produce a standing wave. So microwaves exert strong forces on the electrons emitted by the electron gun, accelerating them to very nearly the speed of light. I believe the previous presentation that we had here said it was about 0.8 C, which is about 80% of the speed of light. Accelerating positive and negative electric charges accelerates the electrons towards the treatment head. Then the radio frequency power acts as a highway for the electrons, whereas the grid pulse is going to be the driving force that pushed the electrons along to prevent gridlock along the highway. So electrons of different velocities are bunched together and then parceled to the catcher cavity. The drift tube is going to be the link between the two cavities. And then here the microwaves are amplified as a result of the kinetic energy of the bunched electrons. Excess electrons go to the anode or to the electron beam collector, where they are converted into heat. The cold water cooling system is used to draw away heat from the system. Within the treatment head, you have the bending magnet, and you also have the target or the scattering foil. With a bending magnet, it directs the electrons from a horizontal direction to a vertical direction. It's usually 270 degrees, but you can also have 90 degrees. And plus or minus 3% energy slits ensure exact replication of the input beam. Then you have, on your way out, is going to be the target. The electron beam hits the target and Bremsstrahlung X-rays are produced. Energy is converted into a spectrum of X-ray energies with maximum energy equal to the incident electron. So the average photon energy of the beam is approximately a third of the maximum energy. Retractable transmission types of target. And we also have high atomic number material in them. Low energy is going to be tungsten, high energy is going to be copper. And then we also have scattering foils. You're going to provide a uniform or a homogeneous beam of dimensions suitable for treatment. Used to produce an electron beam, it's energy dependent and usually made of lead. Then you have the primary collimators. So after emerging from the target, the X-rays are shaped by the primary collimators, which is designed to limit the maximum field size. Then you got the beam flattening filter. Its function is to shape the X-ray beam in its cross-sectional dimension. There is greater intensity at the central axis and less intensity away from the central axis. If you've got a dual photon machine, 2 beam flattening filters are in fact required. Conical medical absorber is also there. Then you've got an ion chamber. 2 independent sealed chambers that are impervious to temperature and pressure changes, so you don't have to worry about those changing or those changing and having an effect on this. And it monitors the beam dosimetry for symmetry in the right, left, and inferior superior directions so that you have more of a homogeneous beam. Or it will tell you if you don't, actually, it's a better way to put that. The ion chamber is going to produce an ionization current that is proportional to the beam intensity, converts information to the control panel as a digital readout or as monitor units, and then terminates exposure if certain criteria are not met. And the field light. The light from the quartz iodine bulb outlines the dimensions of the radiation field as it appears on the patient, allows for accurate positioning of the patient, and must be congruent with the radiation beam. Secondary collimators defines the width and the length of the treatment field, and it's usually denoted by name. Upper and lower inner hour collimators. Nowadays, you're looking at usually X1, Y1, X2, Y2, at least if you're working with variant equipment, that's usually how it's labeled. And they're usually made of lead. You can have independent or asymmetrical collimators, and they'll provide flexible beam definition of symmetrical and asymmetrical beams. Multi-leaf collimators, or MLCs, are designed to reduce the use of lead or CERB custom-made blocks, which if nowadays that's pretty commonplace to have MLCs rather than that, although it can exist in certain places. So the beam stopper, the counterweight. A beam stopper is optional. However, a counterweight is required if no beam stopper is ordered. It may be permanently installed or retractable, and the average transmission of 0.1% of the primary beam. And then, of course, you have the treatment couch where the patients lay down. You can have a bellow-like operation, or you can have a RAM-type patient support. You have the control console on the outside. You have the modulator cabinet. On the control console, your function there is to monitor and control the accelerator and monitor and see what's going on with the patient inside the room. Display types, you're going to have a digital push button panel, video display. Usually the computer is going to be there next to it. You're going to have status buttons, status, standby, preparatory, ready, beam on, whether or not you got an interlock, that kind of thing. The emergency off button terminates radiation and machine functions. In case something goes badly wrong and you need to stop it immediately, that's what you can hit. You also have displays of monitor units, field size, interlocks, that kind of thing. You have mechanical function keys, cursors, and as well as a numeric pad. The mechanical section, and it allows the operator to move the gantry and change the collimators from the keyboard. Function keys, multi-purpose keys coded to execute a logical series of commands depending on the screen's Windows mode of operation. Depending on what's up, then you can hit F4 or what have you, and then you can do what you need to do. Cursor and numerical keypad, and you can use that as a setup key, enter, clear, numerical keypad, that kind of thing. The modulator cabinet. It consists of three major components. You got fan control, you've got auxiliary power distribution, you've got primary power distribution. Turns the fans on and off for cooling as needed. It contains emergency off button that shuts off the power to the treatments unit. This is part of the auxiliary power distribution. You've got a circuit board and you've got a timer for filament displays, the amount of time since the last installation of the Klystron, Thyratron, or in the accelerator gun. You've got a primary power distribution, which contains the major power route to the linear accelerator. You've also got a circuit breaker there. You've got available energies, usually up to 35 MV, although I've never, outside of a proton facility, I've never really heard of this being used, anything that high. These are common photon energies that you'll run across. I have never seen a 21 MeV electron used. Theoretically, it's possible. Half value layers for these two types of energies. You can see there's not much difference, 1.6 and 1.7 centimeters of lead. One thing you can see here is that the amount of dose, or the percent depth dose that reaches into the patient at a certain depth will increase given the size, given an increasing size of the field. So 6x6 for 4 MeV at a particular depth, which it doesn't specify here, but might be 59.8%. You increase the field size, it might increase to 62.7. And 20 by 20 would increase to 66.2. Using a 10 MeV, you can see here that you're going to have much more of the dose present at that same depth, and you're going to have more of it as you go through the higher field sizes. Of course, it's going to depend on the energy, and in order to use an accelerator, you can use it for basically all different therapeutic treatments, even total body or even electron treatments. You've got a wide range of energies. You've got a pretty good percent depth dose. You can treat to several different depths, and you can also do superficial treatments if you wish. They ain't cheap, and they cost money to maintain, and you're going to need good physics support in order to be able to operate it. So those are some of the characteristics regarding linear accelerators.